Here, I want you to look at this picture before we get started. So I'm going to leave you with that for a few minutes here, or a few seconds. And then I'm going to get the lesson started for the day. Okay. So look at this picture. And I'm also going to share the live and say hi to everybody probably in 20 or 30 minutes. I will say hi to everybody. Before that, I'll get the topic for today started, and I'll let you see this first, okay? Give me 1 second. I'll go over here and get my setup going. Also, please do let me know if you can hear me and see everything okay. I'm going to share the live before I get started here because I always forget. Hi, Stephen. Stephen, how are you? And can you hear me? Please like and subscribe. I'll pin that message. Ooh, I'll start a goal. Oh, thank you. Steven says, hear you just fine. Okay. Started a goal. I said, please like and subscribe. Love your story, Steven. I haven't finished reading everything you sent me, but I'm going to go through it and I'm going to share it one of my lives this week. So everybody, look at the picture. We're going to discuss it, and we're going to discuss quantum electrodynamics today. And I'm going to get that topic started and speak for 20, 30 minutes, and then I'll catch everybody's specific messages, chat messages, and questions, comments, thoughts moving forward, so that there is a flow to it. Just getting my live up here on my laptop so I can see what is happening. So give me just a couple more minutes. Okay, so YouTube gives me sort of a live control room these days. So I wanted to get that up and going before I story. Okay, thank you so much, everybody, for being here. Okay. So we spoke about how, let's see, get this over here. So by the way, this is the book that we will be referencing today. It's Cosmology, A Very Short Introduction by Peter Coles. And we will talk specifically about quantum electrodynamics today and have a little bit of a focus on particle physics. Okay, so I will turn the camera on and I will sit down, make sure it doesn't fall over. So, okay, thank you so much for being here, everybody. There is Baji. So, we have been taking some time lately to talk about string theory. Actually, I forgot to share the live, as always. I always forget. I was getting my other settings going. Give me 1 second. Thank you for your patience. Thank you, everyone, once again for being here. Thank you so very much. Really appreciate everybody's presence. It would be amazing if you share your chat messages, thoughts, feelings, comments, and I will get to them later on, probably in like 30, 40 minutes. And I will say hi to everybody and read out your usernames and comments and everything like that in like 30 minutes, okay? I want to first do the topic. So I showed you a picture, and we will talk about that picture. So I'm glad that's already done. You've seen it. And if you're just now joining, please do rewind to go see the diagram we just shared in the live. So you can go back to the beginning part and see that picture. That's what we'll talk about, or related to that is what we'll talk about. And let me share. This is my very special phone that the buttons don't always work. How's everybody doing? I see some people here, Trevor, Jeep. Okay. Stephen, thank you. Okay. Okay. Now. So I wanted to remind you that for a few lives now, we have been talking about string theory, superstring theory. This is not the area of my expertise. I did my PhD in particle astrophysics with a focus on neutrinos and finding ultra-high energy neutrinos utilizing radio frequency techniques or radio astronomy type of things. So even though particle astrophysics is really my area, I've been spending some time talking about string theory, supersymmetry, these types of topics, because the importance of this is really because string theory is a candidate for the grand unification theory, which is a topic of interest to me, makes me very curious, especially because it tries to bring together two parts of physics that are ununified so far, not unified so far, and have some trouble seeing eye to eye sometimes. And these are general relativity on the one side and quantum mechanics on the other side. Of course, particle physics comes out of quantum mechanics. So sometimes people may say that general relativity and particle physics don't see eye to eye, or that these two camps, one is the general relativity camp, the other is the particle physics camp, don't see eye to eye. Now, if quantum mechanics had not been vastly successful in showing results with experiments, then we would not see so much growth in particle physics over the last many, I would say several decades. Really this effort, or what's a grander word, this big grand effort of particle physics got started in the 20th century, where we saw a lot of really interesting developments in both relativity, giving us, of course, new flavor for everything we understood at that point, including a new way of seeing electromagnetism with special theory of relativity, and then a new way of seeing gravitation with general theory of relativity. So with those two types of relativity that Einstein gave us, we really saw and got a much deeper insights into things that we loved and were familiar with, but saw very differently now if we understood relativity. Relativity was also not understood by many people for a while. So even now it might be kind of elusive to people. But basically, electromagnetism had already come leaps and bounds. Electromagnetism had already been contributed to some giants like Maxwell and Faraday, and they had a lot of evidence both in the lab as well as with theoretical equations to describe electromagnetism, which of course is very important because electricity, magnetism, electromagnetism, electric currents, these are all very important. Like we have, light, electricity, all of this going for us now because hundreds of years ago, maybe quite a bit over 100 years ago, more in the 1800s, really. So over 100 years ago, these things were worked on. Okay, but these things were not fully super well understood because when we learned that light is an electromagnetic wave, people were unsure what it meant by that. Basically, what was waving? We knew that electric and magnetic fields could travel through vacuum. We even had this constant, all the Maxwell equations, the electromagnetism equations have certain constants, epsilons and mu's, and the speed of light is a constant. There's different things that are basically going to be giving you expressions for electromagnetism, either in vacuum or in a medium. So either in vacuum or in a dielectric. So we know that electromagnetic waves can just travel through vacuum. There is no stuff or material that's needed. It can, of course, travel through a dielectric medium like ice or salt or water, right? For example, some of the, this is a little bit of a side note, the particle astrophysics particle astrophysics experiments that I'm familiar with, that I come from, as far as my background goes, are always in some kind of dielectric medium. They're set up in some kind of dielectric medium. It can be ice or salt or water. Sometimes we use the sea water, ocean, Mediterranean Sea, right? There is an experiment in there. There's a bunch of experiments in Antarctica because they're utilizing the ice there. So these types of medium are often also leveraged for electromagnetic related experiments, which tells you that, of course, electromagnetic waves can flow through or travel through a medium, but it can also travel through a vacuum. For example, we can see starlight coming towards us. These are light that is hitting our eyeballs from very, very far away objects, like the sun. Even we see that obviously sunlight is traveling through vacuum for about 8 minutes before it reaches Earth. So these types of things were known, but they were not properly digested in terms of what it meant in terms of the bigger picture. How did light really work? What does it really mean for the speed of light to be a constant of nature? So this particular insight that we got, long story short, from Einstein's work of special theory of relativity, where the speed of light in vacuum is a constant, actually gives us this bigger picture and a deeper insight into the relative nature of space-time, into mass energy equivalence. That is what we get from special theory of relativity. And then making that broader and covering more in terms of accelerating frames as well gives us a flavor for gravitation. And not just a flavor, it gives us the updated and the more new way of understanding gravitation. So of course, that is all very important because gravitation is all pervasive. It's a universally present force, phenomena, thing that we experience. Anything with a mass will experience gravitation. So it's good to understand it, of course. It's good when there is a theory or a body of work that can explain it. So that's what we got really with general theory of relativity. But then on the other side, we also saw a lot of developments in quantum mechanics, the physics of the very little, in how to sort of write down wave equations, or just in general, any equations at all for matter at a very, very small scale. So subatomic scale particles, the electron, the hydrogen atom, things that go on inside of an atom. How to kind of explain the physics of small scales like that is what developed also in the 20th century in parallel to relativity uh, and whatnot. And that is really quantum mechanics. And if quantum mechanics um, had not had massive success, like I was saying a bit ago, then it would have been stomped on by the classical physicists. For example, people who would have worked on electromagnetism or gravitation or general relativity, even Einstein, or even some of the people who ended up contributing a lot to quantum mechanics, like Schrodinger, did not did not like the probabilistic nature of quantum mechanics and the uncertainty principle, and how you end up getting, no matter how hard you try, you end up getting probabilities in quantum mechanics, not deterministic results or deterministic answers for things like what physicists were used to at that time. So now, two very beautiful parts of physics. I'm a fan of both, but they did not see eye to eye, and they did not have an overarching theory that unites these two theories, is why we also talk about superstring theory, which is a grand unification theory candidate. It attempts to unify these two parts of physics, general relativity and quantum mechanics. But it is just a candidate because it's not a testable theory. So long story short, we've covered a lot of details over the course of several lives. But if you want to get to the chase here, cut to the chase here, superstring theory, I would just call it a grand unification theory candidate, not a full-blown theory that solves everything about everything, because it's not testable because of its extra dimensions. We won't get into a lot of detail about superstring theory in this live because I promised you quantum electrodynamics and a little bit more focus on particle physics in this live. But if you're interested in superstring theory and what its really issues are or challenges are, or what are the interesting things about superstring theory, which either makes it very interesting and intriguing or kind of holds it back, depending on how you look at it, then we have several lives in the past done on this. So you should go to the live tab of this channel and kind of look through the titles to see which ones have string theory in it, and just watch, play them, see them, watch them, listen to them in the background, whatever you want. But we have covered that as well. So now I wanted to tell you about why superstring theory is motivated. Why such a crazy theory? To some people, quite a crazy theory. What is the motivation? Why is it important? It's because of this type of thing, right? The unification of these two sides not happening, many kinds of attempts being made and still not getting a unified theory, is why superstring theory, with the luck it has had in explaining these two sides, is taken seriously. It's still studied. Okay, so that is that. Now, I also want to talk about the four fundamental forces before I launch into the book and what the book has to say about quantum electrodynamics, because this is all to kind of give you a little bit of background and context. So when we look at things from a particle physics lens, then we must, of course, include and summarize what are the fundamental things. So what are the fundamental forces? What are the fundamental particles, right? Particle physics is a basic part of physics at this point. So it's almost like you should know what are the fundamentals of particle physics. You should know what it's sort of encapsulating. And the four fundamental forces, of course, and we've mentioned these before, are gravitation, electromagnetic force, strong nuclear force, and weak nuclear force. So all of this is to say that when we go to describe what we know about the universe, these are sort of the fundamentals that we are trying to explain. So wouldn't it be so nice if there was a more general theory that not only described the strong nuclear force, the weak nuclear force, or electromagnetic force, but also described gravitation? So once again, for example, to make it more specific, what I mean by unification of the two sides of physics, what I mean is, for example, this. There are four fundamental forces, once again, gravitation, electromagnetic force, strong nuclear force, and weak nuclear force. Wouldn't it be nice to have a beautiful, general, elegant theory of everything that explains all four? Is there such a theory? What is it? And that is what the grand unification theory would be, and that is what string theory has the goal to do, right? And it is a candidate for such a unification. But remember that there were other efforts as well. To some extent, we actually see a unification of the non-gravitational forces. So we've talked about this as well in the past, that actually, depending on the regime that you're in, depending on the energy regime that you're in, the scales that you're in, you can actually unify electromagnetism with strong and weak nuclear forces. So depending on your approach, you can actually kind of unify those. And it was said that there might have been a time early on in the universe after the Big Bang when things were very hot, very dense, very tiny scales, very energetic, very different temperatures. At that point, perhaps they were actually unified. And then then we got a cooling of the universe, then we got expansion in the universe, and and we see that they are manifesting as different types of forces at this point. Electromagnetic force works at a different scale and has a different kind of strength. Strong nuclear force works at a different scale and has a different kind of strength. Weak nuclear force works at a different type of scale and has a different kind of strength. And of course, in particle physics, the force carriers for all of these forces is also different. Electromagnetic force is carried by the photons. Strong nuclear force is carried by the gluons. This is another force carrier particle. The weak nuclear force is carried by the W and Z bosons, another force carrying particle. And so particle physics is basically, again, encapsulating all these different particles. What are the different matter particles? How do they interact? And if there is some force, it's going to be one of these four forces that we just mentioned. Well, what is kind of carrying that force? What is the force carrier particle if you're going to say something is a force, right? So sort of the summary of all of this, like what are the different particles and what are the different forces, and what particle experiences what forces can it experience? Does it interact in this way or not? And if so, what is the force carrier particle? That is sort of the tabular summary of particle physics. And I will actually show you a little table which gives you all this. But, the summary is going to be that there are three types of matter particles. These are leptons and quarks. And then, depending on which one, you'll see who interacts with who in what way. And the force carrier particles I already mentioned are the electromagnetic force would be photons, strong nuclear force would be gluons, and weak nuclear force would be the W and Z bosons. And those are kind of sort of all the particles that have been discovered, that are known, et cetera, et cetera. And again, like I said, depending on the scale, depending on the temperature, depending on the environment, depending on are you close to the beginning of the universe or not, these forces, some of them can even be unified. But what about gravitation? Gravitation is the one where particle physics kind of really struggles. It does not have really an explanation, a natural explanation for gravitation, right? What exactly is gravitation in terms of particle physics? What exactly is the force carrier particle in terms of particle physics for gravitation? So we will see a little bit about what maybe this author thinks about that. And also we will see quantum electrodynamics, because remember, once again, we're trying to come up with more general, more inclusive theories that can explain more things, not less things. If there's some things that are naturally unified by some theory, then we want to learn about that theory. We want to see what that theory has to say, so that maybe that can pique our interest and we can also work on it or draw some kind of conclusion, or at least get a new insight, right? Like, it's not like you have to agree with every single theory or whatever gets worked on. And then the other part is basically, it's always good to still know what is missing, what is something we don't know yet, right? It's good to know what we don't know so that you can go and do your research on something completely novel and maybe contribute to the field, right? So, for example, even though superstring theory is a grand unification theory candidate, I stress that it's a candidate because it cannot be called a successful theory if it cannot be tested, okay? So this thing about the untestability of it, the fact that it requires these extra dimensions and there's not an intuitive answer to exactly why the exact number of extra dimensions it needs is needed. For example, it needs 9 spatial dimensions or 10 spatial dimensions, depending on which one. There's like a couple different string theories. That is not an intuitive outcome. We don't intuitively know why exactly it needs those number of extra dimensions, for example. So it's good to also know what we don't know. Okay, so when we explain or discuss these topics, keep in mind about what people are trying to do. I give you this spiel in the beginning because we want to understand the context of what people are trying to do with these different parts of physics or these efforts, and also what they're trying to unify, what they're trying to bring together, but also to point out the gaps that are still there in physics, okay? So let's see what quantum electrodynamics is. And I showed you that picture of the universe because it's kind of like when we look back, when we see a very large distance away, it's kind of like looking back in time, right? So it's almost like if we could see far enough away in the universe, we might even see the Big Bang. Now, we can't quite see that far back in time. It's like turning back the clock, right? So this picture that I was showing you in the beginning, it's sort of like we are here. The universe is close to 15 billion years old, but of course it was young at one point. It was much less than 15 billion years old at one point. And so what happened in the beginning? So the Big Bang happened, some other stuff happened. There was Big Bang nucleosynthesis. There was, we've got this signature cosmic microwave background radiation from when the universe was around 300,000 years old, 300,000 years old. But in a 15 billion year old universe, or 14 billion years old universe, whichever you like, of course, 300,000 years old is still very early. So we have a signature from when the universe was only 300,000 years old. And then the universe made quasars, the universe made galaxies, the universe made stars in those galaxies. And then we are here, right? We are here. I'd like to quickly say that we are here from some very metal-rich, very beautiful gas nebula, which condensated and made the sun and the planets, of which we're part of the solar system, of course. So, we are here after many stars have lived and died and given us a metal-rich origin story, right? That's why we are here. We're good. We're happy. We have heavier elements, for example, like gold, silver, etc., uranium, things like that, right? Uranium is, obviously has a sad story because of the atomic bomb, but there's some other nice things as well that we've done with heavier elements. So other nicer things, I mean, not other nice things as in whatever. So basically, we are here and we are seeing in the immediate environment some galaxies and stuff, right? So when we look out into the night sky, what do we see? We see stars, but actually most of the things we see in the night sky are galaxies, other galaxies, nearby galaxies. And if you see really far, far away, you might actually see some very special galaxies, and these are called quasars. Quasar, short for quasi-stellar, right? Quasi-stars or quasi-stellars. So if you're ever wondering what a quasar is, that's what they are. And quasars we actually thought were point sources. They looked like stars to us,
but turns out that they're very active, very special types of galaxies whose galactic center is so active, so bright, it rivals the entire galaxy in luminosity, just that center. So quasar is an example of what we call active galaxies. Just so you know, this is another side little tidbit of astronomy. So in our current state of the universe, where we are, where we have formed, right, we have come to be, our evolution supports us people and other things on this planet, beautiful planet Earth, in this solar system with the sun, where we come from a gas nebula that was pretty metal rich, pretty nice, came from other stars dying, making us. When we look around and we see into the night sky, we can see other galaxies, neighboring galaxies. We can see our friendly neighboring galaxies that are not so different from us. We can see some dwarf galaxies, irregular galaxies, the large and small Magellanic clouds, for example. We can also see some pretty special galaxies if we go even farther out, like the quasars, like I was mentioning. At first, when people saw quasars, they were quite confused. They were like, what are these? These look like stars, but the luminosity is so bright and they seem really far away to have that much luminosity. What is going on? Their minds were blown and they discovered quasars, right? And then if you see even farther out, you know, we can't quite see the Big Bang, but we basically look back in time. And we have learned a lot about Big Bang nucleosynthesis. We've seen and picked up on the cosmic microwave background, which is basically leftover sort of photons and light in the microwave wavelength that's hanging out from when the universe was 300,000 years old. So this kind of looking back in time not only gives us sort of a look back in time, but also it means that you're going farther and farther away from us, right? And learning more and more about this universe that we know and love. How much we know it sometimes changes, and how much we love it, well, that's subjective. But let's see what the author says, turning back the clock. The production of the microwave background during the epoch of recombination. So by the way, this epoch of recombination, that's the time. So another way of putting all of this stuff that I was just now saying, turning back the time or turning back the clock, is the universe has gone through evolutions. What the universe is up to right now is different from what it was up to a few billion years ago, maybe, and especially different from what it was up to early on in the universe, right? There were no galaxies early on in the universe. There were no quasars. There were none of this stuff. So quite different things were happening in the early universe. And so we've kind of named the epochs differently. So this cosmic microwave background radiation that I just now mentioned from 300,000 years old of the universe, when the universe was 300,000 years old, there is a cosmic microwave background radiation that we can still pick up on. It is actually everywhere. It's very homogeneous, very isotropic. No matter in what direction you look, you see this. That's from this epoch of recombination, okay? So the synthesis, that and the synthesis of the elements during the nuclear fireball are two major successes of the Big Bang theory. So this is the Big Bang nucleosynthesis that this person is talking about. This author, Peter Coles, is talking about. Big Bang nucleosynthesis basically gave us hydrogen and helium and very trace amounts of lithium. Every other heavier element was made in stars after stars became a thing, right? Before the stars were even a thing, the universe gave us hydrogen and helium, a little bit of helium, and even smaller amounts of lithium. And that is basically Big Bang giving us that. It's nucleosynthesis associated with that early time. The way observations tally with detailed calculations provides firm support for the model. So that's the other thing, that the Big Bang has some firm support supporting it, because some evidence is supporting it, because even now when we measure these things of how much we expect of what in accordance with Big Bang, we actually get the confirmation. So the way observations tally with detailed calculations provides firm support for the model, buoyed by these successes. I always have trouble with that word, buoy, B-U-O-Y. Cosmologists have since tried to use the Big Bang to explore other consequences of matter at very high density and temperature. So another thing is, of course, at this point in the universe, it's not as high density and it's not as high temperature. when the Big Bang was happening and when the universe just got started, it was a very hot, dense, high temperature environment, very different environment than what we see now. Okay, it was called radiation dominated environment. Lots of photons, electrons, positrons actually were sort of in that cosmic soup, if you will, and lots of hot, dense, just crazy stuff going on. We wouldn't have been forming at that time. We are part of the now or a much more current universe. In that past, it was very different. Okay, very, very, very dramatically different. So in that very high density, high temperature environment, in this activity, the Big Bang exploits the connection between the world of the very large and that of the very small. So this is another thing, is that because the environment then was so extreme, it's almost like the Big Bang has this ability to unify the world of the very small and the world of the very big, because the very big was part of the very small at that time. The universe was smaller then, right? The length scales were different. It was hot, dense, temperature, high temperature, all not expanded as much as we are now. So it's almost like everything was part of that same cosmic soup, that it's like everything is more unified at that time. So Big Bang, in other words, is a model that's kind of exploiting that, well, things could have been very, very unified back then, and things are, of course, very different now. So it's almost like a way to explain it away, if you will. The further into the past we travel, the smaller and hotter the universe becomes. The smaller and hotter. Keywords smaller, keywords hotter, right? I already said it was very hot. Temperature's very, very high compared to now. And smaller is the other thing, right? Because at this point, we have expanded a lot because of dark energy. There is this anti-gravity phenomena in the universe that makes it expand. Literally, the distance between 2 points get bigger and bigger over time at large scales in the universe, which is called the expansion of the universe. Dark energy is what is quoted as being the phenomena that enables this. It works against gravity to do that. But back then, long time ago, less expansion, more hot, more small, right? So the further into the past we travel, the smaller and hotter the universe becomes. We are living now at an epoch about 15 billion years after the Big Bang, 14 or 15 billion years after the Big Bang. The microwave background was produced at about 300,000 years after the Big Bang. We know that. I told you the universe was around 300,000 years old at that time. The nuclear furnace did its cooking in the first few minutes. Pushing our understanding of the universe to earlier times requires knowledge of how matter behaves at energies above those achieved in nuclear reactors. So it's almost like we see the matter now, but what they might have undergone back then, well, those conditions were very special, right? So it's almost like, don't ask me to explain it now under these circumstances, when actually it was those circumstances where things might have looked very different, right? So it's kind of the feeling here. Experiments that can probe such phenomenal scales of energy can only be constructed at enormous cost. Particle accelerators such as those at CERN in Geneva. So you might be familiar with the Large Hadron Collider or CERN at Geneva. Which we built, of course, to test out a lot of particle physics phenomena, particle physics theories, etc. To a large extent, of course, we have a lot of success as well with particle physics outcomes and results because of these accelerator experiments. But once again, when you ask somebody to recreate something like the Big Bang, it's going to be very difficult. We cannot attain those types of energies so easily here on Earth in an accelerator. We have come a long way, but there has to be some, limit on people's expectation of how fast that can really be done. So again, particle accelerators such as those at CERN in Geneva can recreate some aspects of the primeval inferno, but our knowledge of how matter behaves under these extreme conditions is still fragmentary and does not extend to much earlier periods in the epoch of nucleosynthesis. So don't ask too much about exactly what happened before nucleosynthesis, because it's too much. We don't know, okay? It's too difficult to know. And we don't live in those conditions anymore. And honestly, we don't know, but we can have ideas. In the early days, physicists saw the Big Bang as a place where they could apply their theories. Now, with theories of particle physics still largely untested elsewhere, it has become a testing ground. So it's almost like the Big Bang Theory, do with it what serves you. If you come at it from a particle physics point of view, go for it. If it does something for you in a cosmology standpoint, go for it. It's there for you. It's a theory. Of course, we cannot go back to the Big Bang in reality, in where it happened, back where it happened so easily. So at this point, just use it to your advantage. And of course, if there is something that can be grounded with experimental outcomes or experimentally observational reality, then of course we would expect that to be confirmed, okay? So now with theories of particle physics still largely untested elsewhere, it has become a testing ground. To see how this has happened, we have to understand the development of particle physics over the last 40 years, okay? So I wanted to read that part, even though I didn't tell you too much about particle physics yet, but we're about to launch into that because I wanted to give you a bit of a background of this particle physics discussion from a cosmology point of view. I want you to understand that there are things that are not known, and people are trying certain things with certain goals in mind, such as unification, such as understanding something at a deeper level, such as unifying something with something else, like particle physics with general relativity, or even within particle physics, having some level of deeper explanation of why things are the way they are. And specifically, just keep in mind about the fundamental forces. If you're ever sort of confused, just know that there are 4 fundamental forces, and 3 of them, the non-gravitational ones, can be unified if you take into account some very extreme conditions, high temperatures, small scales, high energies, things like that. And that's when they're unified. And that immediately points to the Big Bang, right? It immediately points to where, when the universe started, they might have been basically the same thing. So without having some cosmology context, these things don't really make sense. We want to understand it as fundamentally as we can. So without giving you the universe context of why this even matters, I thought it would be incomplete to just talk about particle physics like it's a hobby, although it is kind of a hobby of mine. So, that's really what's going on, okay? So once again, the 4 forces of nature, armed with the new theories of relativity and quantum mechanics, and in many cases further spurred on by new discoveries made possible by advances in experimental technology, physicists in this century have sought to expand the scope of science to describe all aspects of the natural world. All phenomena amenable to this treatment can be attributable to the actions of the 4 forces of nature. So once again, with the 4 forces of nature, which includes, of course, gravitation, which, of course, particle physics doesn't do a good job of explaining, it kind of encompasses everything, okay? That's what we're trying to explain and have a deeper understanding for, is those 4 forces of nature. That's why I keep mentioning them. That's why I've mentioned them in previous lives as well. But those are the 4 forces of nature. We would really like to understand these. And if there is some theory, if there is something that brings us closer to understanding these, then we would be happier as physicists, okay? These 4 fundamental interactions are the ways in which the various elementary particles from which all matter is made interact with each other. So all of the matter that we know, all the ordinary matter, especially because, we can talk about dark matter, and that's another whole topic. And that's also very important in cosmology as well, cosmology, astronomy, and astrophysics. But let's just think about the ordinary matter, what we're made of. Neutrons and protons are what we're made of, okay? Human beings, the periodic table is made of baryons. In cosmology, the word baryons, B-A-R-Y-O-N, is used to describe the periodic table. All of the periodic table, all of those elements, is basically made of protons and neutrons, electrons too, but let's just keep electrons to the side because electrons are very tiny. And a detail is that in particle physics, electrons actually belong to a different family of particles than the baryons. But let's consider baryons. As you keep on adding an extra proton to the nucleus of an element, you get the next element and the next element and the next element and the next, all of the elements, everything we're made of, everything we breathe, eat, excrete, whatever, right, is made of baryons. It's made of the periodic table. And the entire periodic table, starting from hydrogen to helium to lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine to neon to sodium to magnesium to aluminum to silicon to phosphorus. I told you up to 15 atomic number. Everything is just made of protons and neutrons. So let that sink in. So for every heavier element, once you add a proton, you get the next heavier element, right? So 1 proton is hydrogen, 2 protons is helium, 3 protons is lithium, 4 protons is beryllium, 5 protons is boron, 6 protons is carbon. Now, of course, you can also have neutrons. That's less important in terms of chemistry or in terms of the periodic table. Turns out that actually you also have neutrons, depending on and how many neutrons depends on which isotope of the element, blah, blah, blah. And heavier elements, the even heavier elements like barium and up, will actually have more neutrons in the nucleus than there are protons. But as far as the identification, the identity, like the driver's license ID card of an element goes, it's the number of protons there are in the nucleus of that element gives you the element that it is. So if you told me, hey, I don't know how many neutrons there are in this nucleus, but there are 3 protons, that will tell me that it's lithium. If you tell me, hey, I don't know how many neutrons there are or whatever, but there are 20 protons in this nucleus, what do you think it is? It's going to be calcium, okay? So that's the sort of thing that we are made of, that we know and love. And basically, all of the protons, neutrons together make up baryons. And how those things all end up being explained is therefore very important. Particle physics does a job. I don't know, I think it does a good job, but depending on who you ask, it may do an okay job of this. So it turns out actually that protons and neutrons, I've been saying over and over that these make all the elements, that this is what we are made of, you should care about this. But actually, it turns out that protons and neutrons further break down into even more fundamental particles called quarks. Okay, so these quarks are also things that we'll talk about. They also belong to a family of particles. So quarks is the other family of particle. Then there's another family of particle that I alluded to, which is the leptons, and electron is a part of the lepton family. Okay, do you have your PhD? Yes, it's in physics. So leptons is the is the family of particles that electrons belong to. Electrons don't actually belong to the same family of particles as the neutrons and the protons belong to. Neutrons and protons are made up of things called quarks, and these are its own family of particles. And then there's bosons, which are the force carrier particles. Photons are a type of force carrier. Gluons are a type of force carrier. W and Z bosons are a type of force carrier. So understanding these forces, once again, it's like the fundamental forces are the same. It's like the what I just said is the same as understanding the fundamental forces. So we want to understand the fundamental forces because it's all like that's all the forces of nature. We really would want to understand them. If there's something else that's going on, we want to understand that too. If it's unknown to us, of course, we would be like, oh my gosh, well, particle physics is incomplete. We have to add to it. But pretty much of all the things that we understand, know, and love, the 4 fundamental forces is very important. And associated with those 4 fundamental forces are these types of particles and force carrier particles that are also important and summarized by particle physics. In other words, it is called standard model of particle physics. Okay, so this stuff that I just said, the leptons, quarks, and bosons, or the fundamental forces of particle of nature, is actually part of the standard model. And so you might hear, what does the standard model say? Standard model of particle physics is basically this. And standard model of particle physics, unfortunately, does not explain gravitation. So it includes it in the table, if you will, but it doesn't actually have an explanation or a discovery for the particle nature of gravitation or the gravitation particle or anything like that, right? So just letting you know that it's really mostly the non-gravitational forces that are explained by particle physics. Okay, so listen to the rest of this to kind of get this hit this home, if you will. So I have already discussed, or these four fundamental interactions are the ways in which the various elementary particles from which all matter is made interact with each other. So once again, that's the sentence I was explaining, where everything we're made of, everything we know and love, periodic table, everything is basically interacting with each other with these fundamental forces. I've already discussed two of this, electromagnetism and gravity. The other two concern the interactions between the constituents of the nuclei of atoms, the weak nuclear force and the strong nuclear force. So by the way, the strong and weak nuclear forces are the two fundamental forces that we discovered later on, because of course, most people at the ordinary scales will not interact at the nuclear scales where those forces become important. See, as human beings and as classical scales, as far as classical scales go, and by classical I mean Newtonian mechanics, classical physics, electromagnetism, gravitation, general relativity, these are classical physics. They affect scales or length scales that make sense to us. What are these length scales? Like people scales, tree scales, earth scale, moon scale, Grand Canyon scale. These scales, at these scales, classical physics is more of a thing. At those scales, pretty much the forces that we cared about or we dealt with were gravitation and electromagnetism. But then came quantum mechanics. So do you see how it's all connected? Why do we care about the strong nuclear force and weak nuclear force? Why do we now have four fundamental forces? Why do we care about unifying the four fundamental forces? It's because we've also discovered more things. We have discovered the strong and weak nuclear forces, and we have to now explain them too. But why did we discover them? It's because of quantum mechanics. We started to learn and study the physics of the very small quantum scales, tiny scales, subatomic scales, the hydrogen atom, right? Because we were interested in those smaller scales, which is not classical, we had to develop non-classical physics or quantum physics and do a whole, basically develop a whole new field, which is quantum physics or quantum mechanics. And this is where the strong nuclear force and the weak nuclear force come into play. Before that, we didn't even know about them. They weren't even a thing that we really bothered with, okay? So the other two concern the interactions between the constituents of the nuclei of atoms. Once again, the strong nuclear force and the weak nuclear force. The four forces vary in strength. That's the other thing, is that I've been saying how we want a theory of everything, a way to unify these four forces. But guess what? The forces are quite different from each other as we experience them now. Gravitation is the weakest, and it's an always attractive force. So I keep saying how the non-gravitational forces still have some hope of unification, and they have been unified to some extent. You need very extreme environments and temperatures and scales, but they can be unified. But gravitation is kind of quite uniquely different. It's the weakest one as far as strength goes, and it's an always attractive force. There's no repulsion in gravitation, as far as we know anyways, right? Electromagnetism is, for example, sometimes attractive and sometimes repulsive forces. Two charges, if they're oppositely charged, they will attract. If they're similarly or like charged, if they have the same charge, then they will repel each other. So electromagnetic force is sometimes attractive and sometimes repulsive, and has a strength quite different than that of gravitation, and is more strong. Actually, the strength of electromagnetic force is stronger. So the four forces vary in strength. Gravity is the weakest, and the strong nuclear force is the strongest. The strong nuclear force is very strong. It impacts, of course, subatomic, the subnuclear particles, the quarks that are within the nucleus. The protons and neutrons, they interact through the strong nuclear force. So That one's the strongest, and we didn't even discover it until much later. But anyways, and also in the kinds of elementary particles that take part in the interactions they control. The electromagnetic force holds electrons in orbit around atomic nuclei and is thus responsible for holding together all material with which we are familiar. So, strong nuclear force, of course, affects. Oh, my earphone just changed the mode, and I could hear my voice different now. The strong nuclear force, of course, affects what's within the nucleus, but the electromagnetic force, which is less strong than the strong nuclear force, but still a very important force because it keeps electrons in orbit around the nucleus within an atom. So if atoms would not be a thing, if not for the electromagnetic force, right? The electron is opposite charge than the nucleus. See, protons have positive charge. They're made up of further divisible fundamental particles called quarks, and altogether, protons have a positive charge. Because this positive charge is attractive to negative charge of the electron, so then we have electrons and protons kind of staying together, kind of sort of staying together in the atoms. And we have atoms and we have neutral atoms, right? Otherwise, we would just have nuclei. And, depending on the temperature and depending on your energy regime, at higher temperatures and higher energy regimes, like back to when Big Bang was happening, there were no neutral atoms. So if you're just wondering about that, then just forget it. There were no neutral atoms back when Big Bang nucleosynthesis was happening, because things were too hot, too dense, too much energy at that time for electromagnetic force to do anything, and we did not have neutral atoms. But at the energy regime where electromagnetic force can operate, there electrons and nuclei are oppositely charged, so they attract each other. We get neutral atoms. Everything is nice and dandy. This is not always the case, of course. Things can get charged and lose an electron. That's actually how all of chemistry works, is the interchange and electrons going here and there and whatnot. But or say electricity flowing through a metal is because a metal actually has a bunch of sort of free electrons, where the electrons are not so tightly bound to their nuclei. They're sort of not so they're not so tightly married to their nuclei. They're kind of free, and so they flow more freely, and we get electric current, right? But all of this stuff, whether how much electromagnetic force you have or how much you don't have, whether electromagnetic force is a thing or not, will give us neutral atoms or not. So of course, again, very important, right? So very important to understand all this. However, it was realized early in the 20th century that in order to apply Maxwell's theory in detail to atoms, ideas from quantum physics and relativity would have to be incorporated. Because again, it's the theory of the very small, or the physics of the very small. When you go to subatomic levels, scales, length scales, where you're looking inside of an atom or thinking in terms of even the electron, even to actually write down the equation of motion or equation of motion. How is the position of an electron, for example, changing with time? This is actually something that we can think about, right? Because in physics, we love to write down equations for things, and we love to write down equations of motion, for example. We have laws of motion from Newton's. We have laws of gravitation, which is also sort of motion, right? Or the laws of motion of the planets, how we figured out all the things with the Earth going around the sun, all the other planets, what they do. When is Mercury retrograde? When is Jupiter here or Jupiter there or Saturn? Or all, those are all basically coming from equations of motion of the planets. So now think about it, but for the atom and for the electron and nuclei, at those other scales, actually, to get the equation of motion, we would need to incorporate quantum mechanics. We cannot have a classical equation for that. So quantum mechanics gives us, for example, the equation of motion of electron, and it turns out that it's actually kind of a wave equation. We get sort of a wave equation for this thing. We don't get a standard, just boring kind of, oh, the electron is here at this time. No, it's kind of a wave. And on top of that, it turns out that the wave equation is actually kind of giving us the probability of finding the electron at a certain time, not the exactly where the electron will be. So in quantum mechanics, all we get is these wave equations, and they actually give us probabilities of finding the electron. So all of that is to say that you may be interested in understanding electromagnetic force because of all these things, because it's so important. It gives us neutral atoms and makes electricity flow and all of that good stuff. But you cannot ignore quantum mechanics when it comes to these small things. When you try to understand what's happening at the scale of an electron or an atom, you have to remember good old quantum mechanics, or maybe good new quantum mechanics, because at that point, quantum mechanics is not that old in the 20th century. So might have been a little uncomfy for these people, and they had to kind of do some work about it, right? So anyway, however, it was realized early in the 20th century, so in the early 1900s, that in order to apply Maxwell's theory in detail to atoms, ideas from quantum physics would have to be incorporated, and also probably relativity, right? Actually, Dirac turned some of those quantum mechanics equations to include relativity, and they were then relativistic quantum mechanics equations, okay? So it was not until the work of Richard Feynman and others, so now we're getting closer to the title of this life, quantum electrodynamics. All of this was to motivate why we even need such a thing, but hopefully you get the context. So it was not until the work of Richard Feynman, you might have heard of this guy, Feynman. He has contributed largely to particle physics and what we're about to talk about here. So Feynman and others, building on the work of Dirac, I just mentioned Dirac. Dirac is the guy, by the way, who took the quantum mechanics equations and turned them relativistic, that a full quantum theory of the electromagnetic force called quantum electrodynamics was developed. So basically, all of this is to say that we needed a quantum friendly electromagnetic force or electromagnetic force theory or electromagnetic theory, because of basically electromagnetism classically, even though is explained by James Maxwell and others, Michael Faraday, etc. With the electromagnetism equations, we actually have a set of equations, Maxwell's equations, they're called. So classically, we learn a lot and can use these equations, and they pretty much tell us everything about everything. But if you were really, truly interested in understanding things at a subatomic length scale level, then the classical equations are not enough, and you might want to incorporate quantum mechanics into these things, and that is called quantum electrodynamics. Okay, so it's not so scary of a thing. This live is not that scary or not that bad. It's just quantum mechanics in electromagnetism. Okay, so no need to worry. Let me share the live one more time. Actually, I'll take a little breather. 1 or 2 minutes, and then I'll get back to it. So quantum electrodynamics, if you're looking at this live title and being like, what is that? And do I want this? It's very important to understand, why it's even a thing, the context of it. And it's not that bad. It's just electromagnetism, but also incorporating quantum, okay? And it makes sense because electromagnetism, electric currents, what is that? Electrons. Electron is what? Small. So small stuff needs what? Quantum mechanics, because quantum mechanics is the physics of writing things down for small stuff. Specifically, it is the physics or the mechanics. Sometimes it's called quantum mechanics because it's the laws of motion, if you will, equations of motion, equations of states, or wave equation. These are sort of the things that we say sometimes. But all we want to know is, where is this little thing at? Say, what is this thing's position as a function of time? We want to write that down, for God's sake. So what do we do? How do we do it? There's this wave equation way of doing it for quantum mechanics, in quantum mechanics, for tiny small particles that follow quantum mechanics, such as what would be needed in the case of an electron. And that wave equation is generally giving you a probability answer, which is the way of things in quantum mechanics. It's just the nature of quantum mechanics. And that is what needs to be incorporated into electromagnetism as well. So that's what quantum electrodynamics is. And we will read more in just a second. Let me share this one more time. Thank you for being in the live, by the way, everybody. Really appreciate seeing everyone here. Okay, so quantum electrodynamics, okay? Electromagnetism with some quantum included, because why not? Because quantum is important at those scales. Okay, so let's see. In this theory, usually abbreviated to QED. So if you've ever heard of, or if you've ever seen QED, what is that? Like, what does that mean? It's just quantum electrodynamics, okay? And what is QED? It's just electromagnetism with some quantum mechanics included. So in QED, electromagnetic radiation in the form of photons is responsible for carrying the electromagnetic interaction between particles of different charges. So obviously, right, I was giving you the example of electrons because electrons are so important, obviously, in electromagnetic force, or sorry, in electromagnetism as a topic in general, because electrons carry electricity, and we've got equations to describe all that with electromagnetism, equations coming from Maxwell and others. And that's the classical theory. But an electron is a quantum particle. So, of course, we need quantum mechanics to describe it. But another thing that also has a quantum nature is, of course, light. Electromagnetism is electromagnetic waves. Electromagnetic wave is basically light. The classical nature of light is electromagnetic waves. The quantum nature of light is photons. So we already knew that light has dual wave and particle nature. So all you're doing now is just saying, hey, electromagnetic interaction, the force carrier there is a photon, instead of calling it light, and instead of acknowledging only its classical nature, which is light, and wave nature of light. The classical nature of light is wave nature of light. When we regard it as a wave, it's generally at larger scales where it behaves more like a wave. If you are interested in smaller scales where it might behave more as a particle, then we would regard it as a particle. Both natures need to be acknowledged depending on the context. So if you're at larger scales, say radio waves have larger wavelengths. So those, at that point, you can call the thing an electromagnetic wave. If you're at smaller scales, such as gamma rays have smaller wavelengths, at that point, you might call that light a photon or a particle light, a particle of light, instead of the wave nature of light. So once again, depending on context, light too has dual nature. It's called the old quantum mechanics, which Einstein also contributed to, even though later on he became a little bit against quantum mechanics. Okay, so before discussing interactions any further, it is worth mentioning some of the properties of the elementary particles between which these forces act. Okay, so we kind of get what QED is. Now we're going to talk about all the different elementary particles and what is interacting with what in what way, who is interacting with who in what way, all that stuff. The basic properties are particles. The basic properties are particles called fermions. Okay, that's a weird sentence. Fermions are a type of particle. They're a basic type of particle. These are distinguished from the force carriers, the bosons, such as the photon, by their spin. So I told you about the leptons, quarks, and bosons. Another sort of way to categorize particles in particle physics is the fermions versus the bosons. Fermions are matter particles, and they have a different quantum. There is this property in quantum mechanics called spin, quantum property of matter, or any of the particles really, called spin. And this is different for the fermions versus the bosons. So we have actually covered more about what spin is and what it all means in previous lives, especially if you go, I believe it was in the lives where we covered Brief History of Time by Stephen Hawking. We talked about spin, if you're interested, and also in other places as well. But basically, to keep things simple, sometimes people categorize particles in particle physics based on this spin only, and the ones there's fermions with a certain spin, and then there's the rest of the particles or bosons, which have a different kind of spin, and we'll see how it's different. So These are distinguished from the force carriers, the bosons, such as the photon, by their spin. You'll see how it's actually spin 1/2 or a whole number of spin, which distinguishes whether the particle is a fermion or a boson. But we'll keep going. The fermions are divided into two classes, the leptons and quarks. So good thing is that he's mentioning the particle families like I was mentioning before. Once again, all the particle families are summarized by just leptons, quarks, and bosons. Depending on spin, if you want to categorize them, it's fermions and bosons. Fermions are the matter particles, which are basically leptons and quarks. Each of these classes is divided into 3 generations. So now we'll get into the generations, and I'll show you the table that summarizes these generations. Okay, so don't worry about remembering these. We will see them in just a minute. So these 3 generations are, you will see that there are 3 sort of matter generations, depending on the mass, the charge, the color in some cases, you will actually be able to say exactly which particle it is. And we will look at the table in just a second. So anyway, each of these classes is divided into 3 generations, and each generation contains 2 particles. Altogether, therefore, there are 6 leptons arranged in 3 pairs. One of each lepton pair is charged. The electron is an example, while the other carries no charge and is called a neutrino. Boson is spelled as B-O-S-O-N. Boson is a force carrier particle. In particle physics, there are the particles that make up matter, such as leptons and quarks. A lepton example is the electron. A quark example is, for example, the up quark, and quarks are what make up protons and neutrons, which make up all the elements that we know and love. And boson are the particles that carry the forces between all of these other particles. So they are, for example, photon is an example of a boson, B-O-S-O-N, okay? So we'll keep going. One of each lepton pair is charged. The electron is an example, while the other carries no charge and is called a neutrino. So this is, listen to these words. We will summarize really nicely in just a bit, because this is a lot of detail. This is not necessarily how I would present it, but we'll keep going for a bit. While the electron is stable, the other 2 charged leptons, called the muon and the tau, decay very rapidly and are consequently much more difficult to detect. So depending on the lepton of interest. So I said electron as an example of a lepton in the particle family, leptons, because the electron is something we know and love. We all kind of get it. It's what's involved in electric currents, obviously carries electricity. It's in the nucleus of, it's in the atoms of things. All the atoms have nuclei, and then they have electrons, 1 or more, depending on which element. And that's what makes up the neutral atoms, right? If not for the electrons, all the atoms would be positively charged because of protons in the nuclei. So electron is a lepton example that most people know. So it's the most commonly understood and known lepton. But there are actually a couple other leptons that are sort of in that same family as electrons. They're called muons and taus. But these actually decay much more commonly or much faster than an electron. So that's why we don't encounter them as commonly, but they are things. And then there's also another type of leptons in the same lepton family. So think of it as a cousin of the electron. We also see a particle called neutrinos. Neutrinos also have 3 generations: electron neutrino, muon neutrino, and tau neutrino. And these are all within that lepton family. So once again, the lepton family is electrons, muons, taus, electron neutrino, muon neutrino, and tau neutrino, or just neutrinos if you don't want to remember the flavor names. But these are the leptons. Then there's another whole family. So this family chapter closes. Open another chapter for another family. It'll be the quarks, right? And the quarks actually are called up, down. These are what make up the protons and neutrons: charm, strange, top, and bottom. So those are the 6 types of quarks that we see. And then there's, of course, force carrier particles, which are the photons, the gluons, and the W and Z bosons. Photons are the carrier of the electromagnetic force, gluons are the carrier of strong nuclear force, and W and Z bosons are the carrier of weak nuclear force. It's a lot of detail, but this is the summary of the standard model of particle physics that I thought you'd be interested in. So the quarks are all charged, and the three families of them are also arranged in pairs. The first family contains the up and the down. The second pair is the strange and the charmed, like I just summarized. The third contains the bottom and the top. Free quarks are not observed, however. They are always confined into composite particles called hadrons. So a hadron's example would be the proton or the neutron, for example. These particles include the baryons, which are combinations of three quarks, the most familiar examples of which are the proton and the neutron. So again, the baryons, like I was mentioning, is a composite of quarks. The most familiar ones are, of course, the protons and the neutrons, and these are the ones that we know and love. And pretty much in cosmology, that's what people mean. They mean the protons and neutrons generally when they mean baryons. There are many other hadron states, but most of them are very unstable. So you might make these hadron states, which are composites of quarks, but if they're super unstable and you never meet them in real life or in nature, then it might not be something that you want to deeply study. They might be produced in accelerator experiments, like the ones we've set up, for example, at the Large Hadron Collider, et cetera, or in the Big Bang, but do not hang around for long before decaying. So unfortunately, a lot of these more exotic particles, if you will, in the particle physics summary called the Standard Model of Particle Physics, include particles that they don't hang around for long. They decay within a short time. And so because they decay, we would not really see them too much, encounter them too much. Using our current understanding, it seems that within 1/1,000,000th of a second of the beginning of time, quarks have sufficient energy to tear themselves free. At earlier times than this, the familiar hadronic particles dissolve into a soup of quarks. Each of the fermions also has a mirror image version called its antiparticle. So you might remember we talked about like two, basically a pair at one point, and that's because all of these particles, all these fermions actually also have antiparticles. In a sense, never mind. I was going to say something else, but it's not important right now. But anyway, each of the fermions also has an antiparticle. It's sort of a mirror image particle, like a pair partner, basically. And this is an antiparticle. So this is not to be confused with the supersymmetry super partner particle that particles may also have, which is what the concept of supersymmetry theorizes. But this is antiparticle. This is well within the realms of standard model of particle physics. Okay, so for example, electron antiparticle is positron, and that's been seen. It's a thing. It's definitely possible in nature to have a positron. There are more processes that make electrons than do positrons. So we have more electrons generally than positrons. But antiparticles are nothing so bad, nothing too exotic or weird. Just a partner of these particles. Okay. The antiparticle of the electron is a positron. There are also anti-quarks and anti-neutrinos. So sometimes within a particle physics interaction reaction process thing, you might get out the particle or its antiparticle, but the flavor would be one of those flavors that we just talked about. Like it could be an electron, a muon, or a tau, or it could be an anti-electron, an anti-muon, or an anti-tau. Where if it's an anti-electron, we would just call it a positron, or it could be a neutrino that's involved somewhere in some process. But actually, when it does something, it becomes what comes out is an anti-neutrino. For example, you might see sometimes it's denoted with like a bar on top of the symbol. Okay. The theory of QED describes interactions between the charged fermions. Right. So quantum electrodynamics, of course, we're talking about electrodynamics or electromagnetism with quantum mechanics included. So, of course, electromagnetism, it's important between charged particles, right? If there's not a charge, then there is no electromagnetism. There's no electromagnetic force. And so out of all the particles, whoever has charge, whichever ones have charge, are going to interact with the electromagnetic force. So it's going to be like you need to have QED or quantum electrodynamics for these particles that have charge, because they have electromagnetism as well as quantum in their life, basically. Okay, so that's one way to kind of think about this. Okay, so the next force to come under the spotlight was the weak nuclear force, which is responsible for the decay of certain radioactive materials. The weak interaction involves all kinds of fermions, including the neutrinos, which, being uncharged, cannot feel the QED interaction. So, by the way, I was mentioning just now that QED is, of course, important when you have charge. Well, guess what? There are particles within the lepton family that don't care about QED because they don't have a charge. They just could not care less. And these are neutrinos. These are the type of particles that I actually worked on in my thesis, or they were involved in my thesis. They were the sort of main character particle in the particle astrophysics that I worked on. But basically, these are what we call very introverted, much, much lighter cousins of the electron, belonging to the same family called leptons. But they don't have a charge, and so they don't interact with electromagnetic force. They don't have that electrodynamics that we might want to talk about otherwise for other particles. So QED, quantum electrodynamics, nothing of that nature needed. For neutrinos, how lovely. They just don't care because they don't have charge, okay? So again, but they do interact with something else. They interact with through another type of force. This is called the weak nuclear force, one of the fundamental four forces, four fundamental forces, but they do not care about electromagnetic force, okay? So the weak interaction involves all kinds of fermions, including the neutrinos, which, being uncharged, cannot feel the QED interaction. As in the case of electromagnetism, it's almost like the neutrinos are kind of blind. They don't have charge. It's like they don't see certain things. They don't see certain things, and so and that thing in the case of neutrinos is electromagnetism. How must be lovely, right? Must be lovely. It's almost like they're unbothered. They're unbothered by QED. QED, you can just exist. I don't care because I'm a neutrino. I don't care about QED, is what the neutrino said. Okay. As in the case of electromagnetism, weak forces between particles are mediated by other particles, not photons, but in this case, by massive particles called the W and Z bosons. So once again, electromagnetic force is carried by photons. This is the light particle, as in the particle nature of light is the photon. The quantum nature of light is the photon. It carries the electromagnetic force. When there's two things with charge on them, when there's two particles, such as the electron and proton being a composite of quarks, then there is then there is electromagnetic force between those things, and it's carried by photons. But what about those particles called neutrinos, who interact through the weak nuclear force, and they do not care. They're unbothered by electromagnetic force. There is something else that carries that weak nuclear force, and these are the W and Z bosons. Again, these were kind of discovered a bit later because the weak nuclear force did not come up right away when all of this was going down. And so what are these? The W and Z bosons are also examples of, first of all, bosons. Somebody was asking about bosons. These two are in the boson category of particle physics. Okay, so again, the particle families are leptons, quarks, and bosons. In the boson family, there's photons, which carry the electromagnetic force. In the case of neutrinos, which are leptons, but they interact through the weak nuclear force. This is carried by the W and Z bosons, which are massive particles. They're not like photons. Photons are actually massless. The fact that these particles have mass, unlike the photon, is the reason why the weak nuclear force has such a short range. and its effects are confined to the tiny scales of an atomic nucleus. Isn't that so crazy that that photons are massless? So it's like their effect can go a larger distance, but W and Z bosons are actually quite massive compared to the photons. And so their effect is very short range. Again, it's a subatomic range kind of effect, right? Weak nuclear force. So anyway, weak nuclear force is mediated by the W and Z bosons. They're massive bosons. The W and Z particles otherwise play the same role in this context as the photon does in QED. They and the photon are examples of what are known as gauge bosons. The theory of the strong interactions responsible for holding the quarks. So now we come to the strong nuclear force. So we've talked about gravitation. We don't understand it in terms of particle physics. Okay, it's a deficiency of particle physics to where we don't really have a theory or an understanding of gravitation with particle physics, but we do have an understanding of gravitation with general relativity. Thank you, Einstein, and thank you, God, right? Coming to the next electromagnetic force, the next fundamental force, which is electromagnetic force, this is mediated through the force particle called photons. Yay, light particles or quantum nature of light will carry that. Then we talked about the weak nuclear force. This is mediated by the force particles called the W and Z bosons. And this force affects, for example, the neutrinos who only interact actually through this weak nuclear force. They don't care about electromagnetic force, for example. Last is strong nuclear force. Who carries this force and what does it affect? The theory of the strong interactions responsible for holding the quarks together in hadrons. So remember how quarks were always in these composites called hadrons or baryons, depending on if it's the very common and familiar type of quark composite like protons and neutrons that we all know and love in our atoms that we know and love. Then those are called baryons. And the theory of the strong interactions that keep these quarks together is what the strong nuclear force will deal with. So the theory of the strong interactions responsible for holding the quarks together in hadrons or baryons is called quantum chromodynamics, QCD. So we just mentioned QED for quantum electrodynamics, the things that interact with both electromagnetism as well as they're at a quantum scale, so you need QED. Now we just mentioned quantum chromodynamics or QCD, something to do with color. There's another property that we haven't talked too much about. It's called color. So the theory of the strong interactions responsible for holding the quarks together in hadrons is called quantum chromodynamics or QCD, and it's built upon similar lines to QED. In QCD, there is another set of gauge bosons to mediate the force, and these are called gluons. So kind of like gluons are very strong. They're going to keep the baryons together. So of course they have to be very, very strong. So these are called gluons. There are 8 of them. Oh my gosh. There are 8 of them. In addition, QCD has a property called color, which plays a similar role to that of electric charge in QED. So basically, if you take QCD and QED together, there are certain properties that are kind of transpiring, as you can see, as we are mentioning them. These are basically mass, charge, and color. Depending on which particle you are, or basically, if I told you the mass of something, the color of something, and the charge of something, you would basically then give me the answer, okay, you're talking about this particle. I'll show you the table of particles really soon here, but basically depending on your mass, charge, or color, you would tell me that it's an electron, or you would tell me, oh, it's this neutrino that you're mentioning, or you would tell me it's this quark. So depending on those, and actually that another property too that I should mention is spin. So depending on mass, charge, color, or spin, these are all quantum properties, quantum states, if you will. All of these particles that we have just now mentioned, I know quite a few of them, and we will summarize them all in a nice table very soon. I'll show the picture of the table. But all of these particles, all of them, they sound like there's a lot of them, right? And this is one of the complaints of classical physicists, which is that particle physics just has so many of these particles. And, it seems like this jungle of particles, and people want to know sort of what is the broader picture, the bigger picture that can explain all of these particles. That is a complaint of classical physicists. For example, when people were trying to come up with, for example, a grand unification theory, something that they would like to address is this particle jungle. There's just so many particles and so many states and properties and whatnot, and we just don't want to deal with it in this way. And can we have a bigger picture way of dealing with this, a theory of everything, right? But keep in mind that everything that we understand or have measured or know about these particles that we just mentioned so far in this live, those have to all fall out of this new theory. If there is a grand unification theory, everything that is known already by particle physics has to kind of be outputted by that theory. You can't just have a theory which then does not give you the fermions or the bosons, or it just leaves out something maybe like color or quarks or something, right? Everything has to be explained by this grand unification theory, which actually makes it quite challenging. Because as you can see, as much as the particle jungle can be inconvenient for people who don't want to deal with a lot of different variety, but at the same time, it's also known things. And if you don't have a grand unification theory outputting the known things, then you cannot accept that grand unification theory as the reality. Okay, so that's what's really going on here with the grand unification theory and its challenges. Partly the challenge is, there are other challenges too, but partly the big challenge is that it really has to explain all of these quantum properties as well that have been found and delivered by quantum mechanics and particle physics. So namely, once again, the mass, the charge, the color, and the spin of these different particles that we've just now mentioned have to all come out of a grand unification theory. Better do if you're going to explain and call something a theory of everything, okay? So I'll tell you a little bit about the electroweak theory because he talks about it next, and then we'll leave it there. The drive for unification is the next topic he discusses because it's the natural next topic. And this thing that I just said is literally what's kind of going on here. Like once you have all these particles, and I'll show you in the table, right? We've discussed leptons, we've discussed leptons, we've discussed quarks, we've discussed bosons, and the different flavors of each one. So electron, neutrinos, quarks, bosons, all of these are the different particles, and there's different types of them in each of these families. And they all have a mass, a charge, a spin, and a color. A grand unified theory, once again, has to explain these, and things better be falling out of the theory naturally to encompass all of these, okay? Is it possible, taking a cue from Maxwell's influential unification of electricity and magnetism in the 19th century, so in the 1800s, to put all QED, the weak interactions, and QCD together in a single overarching theory? This is what the grand unification theory motivation is. A single overarching theory. A theory that unifies the electromagnetic force with the weak nuclear force was developed around 1970 by Glasgow, Salam, and Weinberg. Can you still hear me? Called the electroweak theory, this represents these two distinct forces as being the low energy manifestations of a single force. So indeed, there was some success in unifying, of course, the weak nuclear force with electromagnetism force. Electroweak theory, which represents these two distinct forces as being the low energy manifestations of a single force. When particles have low energy and are moving slowly, very slowly, they do feel the different nature of the weak and electromagnetic forces. Physicists say that at high energies, there is a symmetry between the electromagnetic and weak interactions. Electromagnetism and the weak force appear different to us at low energies because this symmetry is broken. There is another symmetry at high energies, that is something we're not, there's Baji, that we're not it's something that we're not constantly experiencing because we live in a different reality than at those high energies. But there is more beauty of symmetry to be found at those other environments. Okay, imagine a pencil standing on its end. When vertical, it looks the same from all directions. A random air movement or passing lorry will cause it to topple. It could fall in any direction with equal probability. But when it falls some particular way, picking out some specific direction. In the same way, the difference between electromagnetism and weak nuclear forces could be just happenstance. Wow. In the same way, the difference between electromagnetism and weak nuclear forces could be just happenstance, a chance consequence of how the high energy symmetry was broken in our world. Oh, how sweet. Oh, how sweet is that? Oh, how cute is that? Basically, this is another complaint of the classical physicists, by the way, which is that there's all these numbers, all the mass, charge, spin, color, or even the strengths of the different forces, or the different numbers that are of importance in particle physics, all kind of seem to be a little bit very specific, very kind of like, why is it that number? Like, what's the overarching theory or explanation for why something is what it is? And it could be something like this, where it's sort of this happenstance way, a chance consequence of some high energy symmetry that was broken, which could be the explanation, which I kind of like, honestly, because one would question why this number and not that number, why this but not that, and then probability kind of comes to your rescue, which I find to be kind of entertaining. That in quantum mechanics, the thing that pretty much turned people against it is also something that will kind of save you a lot, which is the probabilistic nature of quantum mechanics. Probability, uncertainty are things that we have to know and love in quantum mechanics and at these scales. So it could very well be just happenstance, chance, symmetry breaking in that particular way. Wow. The electroweak and strong interactions coexist in a combined theory as well. So as I told you earlier, the non-gravitational fundamental forces have been unified. Here he is. He's sleeping. And they have been unified because of taking into account that they may have been the one and the same or very unified in a very different environment, such as the beginning of this universe. Okay, so once again, it's been the electroweak and strong interactions coexist in a combined theory of the fundamental interactions called the Standard Model. It's an amazing success that all the principal particles predicted by the Standard Model have now been discovered. Thank God, right? Good thing with that. At the time of this book, apparently the Higgs was not discovered. So he's saying all of the principal particles predicted by the Standard Model have now been discovered, with only one exception. A special boson called the Higgs, ooh la la, is required to explain the masses in the Standard Model, and it has so far defied detection. Oh my gosh, this book is a little old. The Higgs boson too has been discovered now. The Higgs boson was discovered in 2012. Seems like a very long time ago now, or kind of short time ago, but actually is a long time ago. Wow. So the Higgs is what gives people, and by people I mean particles, their mass. And at the time of writing this book, it was not discovered. It was the one missing boson, the one missing little particle. Oh, this model, however, does not provide a unification of all three interactions in the same way that the electroweak theory does for two of them. Physicists hope eventually to unify all three of the forces discussed so far in a single theory, which would be known as a grand unification theory. By the way, I would consider something a grand unification theory if it also, of course, unified gravitation. Can't forget that one, but oh well. There are many contenders for such a theory, but it is not known which, if any, is correct. Because, by the way, another thing with unifying the three non-gravitational forces, I do believe required supersymmetry as well. So we kind of read that from the other book called The Elegant Universe by Brian Greene. And it turns out, if I remember correctly, and if I understand correctly, that to unify even the three non-gravitational forces, you actually needed supersymmetry or SUSY. And if SUSY is not discovered yet in a experimental sense, of course, it's been theorized, but if there is no evidence of SUSY in the colliders or something that tells us that supersymmetry is real and particles have their superpartner particles as well on top of everything else, then it would be a little difficult to unify the non-gravitational forces, okay? So another thing where I wanted to point out that we know that we don't quite know that, okay? It's important to understand what we don't know and to know what we don't know so that we can then proceed and do the research to maybe know that, okay? One idea, he's talking about supersymmetry next. Wow, it's like I'm a psychic, but actually not. I'm a physicist with apparently psychic abilities. One idea associated with unified theories is supersymmetry. According to this hypothesis, there is an underlying symmetry between the fermions and the bosons, between them. Because remember, if you came to our string theory chats, remember how string theory too is saved by supersymmetry, or SUSY, Susie Dooby Doo. Susie Dooby Doo, where are you? We hope that we find you in the Large Hadron Collider or somewhere of importance. Basically, there was a problem, if I remember correctly, in the 1960s or 70s where string theory was only explaining bosons, like it was a bosonic string theory. They called it bosonic string theory, obviously, if you don't explain the fermions, right? Like you might have called it string theory and then you ran and edited to put in the word bosonic string theory because you realized that, oh gosh, this actually does not cover fermions. Whoopsie daisies, right? But what kind of saved it, what kind of saved the day back then also was this supersymmetry concept, the concept of supersymmetry or SUSY. So supersymmetry is quite important. I hope it's discovered or something, because I mean, I think string theory would really suffer and the unification of the non-gravitational forces too. You know, anyways, according to this hypothesis of supersymmetry, there is an underlying symmetry between the fermions and the bosons, two families which are treated separately in the standard model. So as you may have picked up on, the fermions and the bosons, B-O-S-O-N, the fermions and the bosons are different because of their different spin. And they're treated differently too. They're treated differently too in the standard model. But this supersymmetry business basically theorizes that every fermion has a boson partner and vice versa, a super partner, if you will. Basically, supersymmetry as a theory gives all the particles a super partner particle. Quarks have bosonic partners called squarks. Neutrinos have sneutrinos and so on. So leptons superpartner would be sleptons, okay? And this is real. This is real, like as in the theory is real. Whether we find them is a different matter. Experimentally, I don't know of, SUSY particles being found. But the theory basically suggests that all these particles have a supersymmetry super partner particle. So lepton would have a super partner particle called slepton. Quarks would have a super partner particle called squarks, and so on, okay? One of the interesting possibilities of supersymmetry is that at least one of the myriad of particles that one expects to reveal themselves at very high energy might be stable. one of the interesting possibilities of supersymmetry is that at least one of the myriad of particles that one expects to reveal themselves at very high energy might be stable. Could one of these particles make up the dark matter that seems to pervade the universe? So then he's connecting it to dark matter. So a lot of people, a lot of theoretical physicists want supersymmetry to be real, okay? Because supersymmetry, as theorized, kind of saves the day for a lot of things, especially to unify the non-gravitational forces as far as I understand. And also it saves the day for string theory. That's why it's called superstring theory once it takes into account supersymmetry. Without supersymmetry, it would be kind of hard for string theory to do its business. And so, of course, they want SUSY to be real. Of course, they want evidence of SUSY to be found in experiments and things like that. There he is, sleeping. He has a super partner too. She's upstairs. So slept on. So my advisor, we started working on a slept-on paper at one point. I think it didn't get published, but this is all very real. Sort of a search for super partner particles could be, and if that leads to something, could be very exciting for a number of folks, for a number of theorists. And this author, Peter Coles, of this short little book on cosmology, is also connecting it to possibly dark matter. What if SUSY particles are a candidate for dark matter? Woo, woo, woo. Like that could be really, really cool. Okay. So those are some of the very cool sort of implications of supersymmetry. And once again, supersymmetry is kind of needed in order to unify some of these fundamental forces that we spoke about, pretty much all of them, actually, because the three non-gravitational ones needed, and string theory, which is a grand unification theory candidate for all of them, including, of course, gravitation, which is sort of neglected in particle physics, if you will. It's not that particle physicists are wanting to neglect gravitation, but they just seem to end up neglecting gravitation and does not explain gravitation within particle physics. Well, if you have a candidate theory such as superstring theory, that too requires supersymmetry. So this is why we actually spent some time talking about supersymmetry in the past as well. And with that, I will actually take your leave now. Thank you so much, everybody, for being here. In fact, I will not take your leave just this second because I will show you that picture I promised and maybe read some of these comments on my laptop, okay? So I'll scroll up and read your comments on the laptop to see if there's any questions, and I'll show you this table of particle physics, particles that we just now talked about, and give you the summary. Okay. So let me do that right here, right now. By the way, as we talk about supersymmetry, super partner particles, and SUSY and super all of that, could you please do a super chat? That would be most amazing to keep this channel going and to support the efforts of this channel. That would be most amazing. Much appreciated. I'm going to turn the camera now to show you the particle physics summary here of all the particles. And I will be looking at your comments on my laptop as I scroll up so that I don't disturb the camera view here. And thank you so much, everybody, for being here and for all your questions, comments, thoughts, dreams, and wishes. Stay safe, take care, and I will rotate this and still hang around here for a bit, okay? There's my microwave. Okay. And here's the chickpea container that you were on. And there it is. Here's the elementary particles. Here's the leptons that we mentioned. For example, the electron is a type of lepton. Then we have in that same family, we have muons and taus. These are heavier than the electron and they decay much faster than the electron. So you might not encounter them in nature as easily. Then we have neutrinos. We have the electron neutrino, the muon neutrino, and the tau neutrino. These are also leptons, and these are
in the same family. Oh my gosh, did someone do a super chat? Oh, thank you, Acacio. Let me thank you properly in just a second. Let me keep going for now. So in the family of leptons, we have electrons, muons, taus, electron neutrino, muon neutrino, and tau neutrino. So those are the leptons, of which the most common, of course, is electrons. And you probably are very familiar, but keep in mind that along with electrons in the lepton family, we also have muons and taus. These are heavier than the electron, but they also decay a lot faster than the electron, and so you might not see them out and about in nature too often. And then we actually have these very elusive particles that are also in the lepton family called neutrinos. There are 3 flavors of them: electron neutrino, muon neutrino, and tau neutrino, all kind of form the lepton family. Now, the electron, muon, and tau, of course, have charge. So because they have electric charge, we namely have quantum electrodynamics. Of course, they both have quantum effects as well as electromagnetism effects between them. And so we developed this thing called quantum electrodynamics to describe the interactions of electrons, muons, and taus, because these things have charge. The neutrinos right here, see in this little row right here, all these neutrinos, each of these getting this like new symbol. The V looking symbol here is called the new Greek letter. And see how these are all neutrinos, 3 different flavors of neutrinos. None of them actually have an electric charge. So they don't care about quantum electrodynamics because they don't interact with electromagnetic force. They actually interact with something called the weak nuclear force, which we also mentioned. Then coming to the quark family right here, this is the quarks family. See, these 2 rows of particles are the quark family of particles, and we have the up quark, the down quark, the charm quark, the strange quark, the top quark, and the bottom quark. Those are all the types of quarks. These end up being composite particles called hadrons or baryons. The quarks generally are not, generally speaking, hanging out by themselves. They create or they form composite particles along with other quarks. For example, the common ones that we know and love are protons and neutrons. These are the baryons that we are very familiar with. Protons are made of up and down quarks, and neutrons are also made of up and down quarks, but in different sort of different ratios. It's like an up, up, and down, and a down, down, and up. There's a difference in exactly which exact quarks, but it's a mixture of the up and down quarks is what's in both of them, neutron and proton. I sometimes forget. Is the proton the up and down, and the neutron down, down, and up? Is that right? Somebody can correct me in the chat, but pretty much I just know that the protons and neutrons are both made up of these 2 types of quarks. So these are the matter particles that we just spoke about. Okay, so we talked about the leptons and the quarks just now, and see 3 generations of matter, kind of meaning that the masses of these things actually go up when you go from the 1 to the 2 to the 3 generation. Okay, so like electrons are lighter than muons, muons are lighter than taus. Up and down quarks are lighter than charm and strange are lighter than top and bottom quarks. So these are these particles. But again, pretty much the issue is that you might not meet a lot of the heavier particles that we're mentioning here in the elementary particles of particle physics, because they may decay too fast, and so you won't encounter them too much. Then we come to the force carrier particles. So somebody asked about bosons. These are all the bosons. So if you just kind of ignored all the matter particles and you come to just the force carrier particles, these are the particles in particle physics that carry the different forces, the different fundamental forces. In fact, these are the ones that carry the non-gravitational fundamental forces. There are 4 fundamental forces, including gravitation. Keeping gravitation to the side because we don't really understand it in a particle physics way yet, we see these 4 force carriers. 2 of them carry the same type of force, and that's why we have 4 force carriers here, but 3 fundamental forces that are being covered by these. So photon at the top is what carries, of course, electromagnetism, electromagnetic force. That's a fundamental force carried by photons. Then we have gluons that carry
the force strong, nuclear force, another fundamental force of nature. And then we have the Z boson and the W boson right here, Z and W. These Z boson and W boson actually carry the weak nuclear force. That's another type of fundamental force of nature. In fact, neutrinos, the ones, the particles in the lepton family we mentioned earlier, these three interact through the weak nuclear force. They don't interact through anything else. Okay, within this description, as you can see, their electron, the electron, for example, as a lepton, will interact with it with electromagnetic force, so it can interact with the photons. It can actually also interact with the weak nuclear force. But neutrinos only care about the weak nuclear force. They do not have a charge. They do not bother with the electromagnetic force. So depending on which particle you interact through multiple of these force carrier types of particles or forces, or just the one or one type, right? So that's something as well. Pretty much they actually, I was going to say, pretty much they all, no, I can't really say that sentence. It wouldn't be correct. Basically, I was going to say that if you have a charge, of course, you interact with electromagnetic force. So neutrons, protons, quarks, all of these quarks with their charge would interact with photons through photons. Electron does that too because of it being charged. But the neutrinos really, truly, they don't have a charge, so they don't interact through the electromagnetic force. It also makes them kind of challenging to detect, actually. That's a whole another topic. I studied particle astrophysics. In that particular topic, you actually care about this a lot because neutrinos are weakly interacting, or they interact only through the weak nuclear force. Makes them very, very difficult to detect, makes them a huge challenge, but also makes them a rather good messenger of astrophysical phenomena because they don't interact with magnetic fields, electric fields, whatever, along the way when they're coming from some distant source to us here on Earth. So again, makes it a very interesting particle, very elusive particle nonetheless. And actually, by the way, while I'm at it, the neutrino was also a dark matter candidate. So we saw how there's an interest in unifying all of these things together, especially also in unifying gravitation with the fundamental forces of particle physics here in this table. But there are some challenges, and we saw how supersymmetry is kind of needed in order to solve some of those challenges. And so we hope that supersymmetry is real. But if it's not, then that too is nature giving us an answer, and we have to accept it. And I guess it would topple superstring theory, so there's that. But anyways, I will let you review this and ask any questions. Thank you so much for being here. Thank you for the super chat. Anybody else, if you want to support these efforts and the channel, especially the physics classes and physics discussions. Hopefully these are fun discussions and not just a boring class. And hopefully, you can learn a lot in a digestible way presented with these types of discussions. We really appreciate your support. And if you want to do a super chat, super thanks, PayPal link in the bio, all of that stuff is most welcome. Thank you so much. And I will scroll through and see your comments now on my laptop. Thank you. You might hear my water drinking. Oh, and I forgot to. Acacio, thank you so much, my friend. Acacio did a super chat. Thank you so much, Acacio. Muchas gracias. Thank you so much. Wow, thank you so much. Thank you for the kind comments and the super chat. Acacio said you were outstanding. Oh, thank you. Gave a super chat. Thank you. Thank you, everybody. Where's your cat? So he's right there on the cat tree right there. We're looking at this page right now, but we showed him, intermittently. He was behind me on the cat tree. And if you, so by the way, if you're joining
late, or if you're joining now, I mean, no worries at all. Like, there's no late. You can just rewind the live, hopefully. Please do rewind to see the full live. Thank you so much. And at the very end, we can also show Baji again, actually, because he is still here. He was behind me on the cat tree. Somebody asked, Akash asked, is there a Higgs boson 3D? 3D? Are you asking about a picture, or are you asking, is there a Higgs boson? I don't know if I follow that question, what that means. Hi, Baji. Baji is here. Baji, Fuji, Suji. Thank you, universe, for my children who are cats. Oh, let me show you Baji. Oh, hi, Baji. Hi, Baji. Yeah, I get the three-dimensional thing. I'm just not, can you, yeah, I don't know. I don't know what the answer is. Jeep says three-dimensional. Cassio says you're welcome. Don't forget to mention Madagascar. Of course. Thank you so much, Africa. Thank you so much, Madagascar. Thank you so much, Australia, New Zealand, Asia, Europe, North America, South America, Antarctica, and hopefully I've covered all the continents that we're joining tonight or later. If you see this as a video upload later on, we do appreciate your support so very much. Please do leave us a like, a subscribe, a comment. All of it is much appreciated. A super chat, a super thanks, a super anything. And we also have a PayPal link in the bio if you want to support the channel of Cats and Physics and buy Baji a treat and things like that. So thank you all so very much. And here's Baji Baba. Hi, Baji. Hi. Hi, Shona. Baji Baba likes to show his engagement in the live as well. Mommy just did a little physics class. How did you like it, Baji? Baji says that he read all that and he studied all that. Oh, somebody asked, what book are you reading? Okay, I'll show you exactly what book right here, right now. So next to this low sodium chickpeas is the book that we've been using here. So, I mean, some of the books, some of the other books are here too, but here's the book. It's called Cosmology, A Very Short Introduction by Peter Coles. It's quite a nice book. I found it to be quite cute and summarizes some of these things really, really nicely and whatnot. And so here's the page I was showing, the building blocks of matter. Here we go. And here's another little kitty cat right there. Thank you all for your support very much. Here's Sachi Mama, Suji. This little girl right here, thank you, universe, is called Sachi Mama, or Suji is her official name. And here is Baji. Hi, Baji. Hi, Baji, are you happy? Are you happy? Somebody asked, what does Baji think of all this? I think Baji is just happy, and Baji is loved. Sharn was here. I'm not sure what he or she asked. Hello, Stephen. So I'm going to cover Stephen's page of from his book that he sent me one of these days very soon here. It might be in just the member specific content though. So we might do a page here and then a members only for his book. Omran says, what about quantum quasi mode? When did physics write stuff down? Hi, Parrot. I'm going to say hi to everybody now that I have a chance. Hyal, Parist TV, Stephen, Big Frank, Jeep, Acacio. Doro says pronounce. I don't know what he meant. Encompass. What is that bad? Mohammed, Big Frank, Baby Baba. Thank you so much for being here. Nathan was here. Hi, Nathan. I'm up way past bedtime. Oh, gosh. Looking great. Thank you. Hi, Chickpea. I don't know if Chickpea was here. If you were, hello. Hi, our India. Hi, Dieghost. I don't know if you guys are still here, but I'm saying hi now. Let's see. Let's see. Here's Sachi's down on the coffee table. Hi, Cat. Okay, I think I see mostly everybody's comments. Everyone, thank you so much for visiting tonight. Thank you so much for being here and being part of the discussion. Love it. Baji, aw, Baji looks happy. Yes. Acacio. What did Acacio say? Thank you. Thank you so much, everyone, so very much. As always, really appreciate everybody being here and participating. Thank you once again. Have a great night, everybody, and see you tomorrow. Good night and sleep tight, my friends. And yes, if you're seeing this as a video upload later on, no worries. If you missed the live action, then, well, see the live as a live replay or video. And I look forward to seeing all of your comments later on when I wake up. So